Right. Let's go ahead and get started. I'm going to do a little bit real quick with some diode logic gates and then talk more about the flip-flop logic gates. So there's two different logic gates here. They're just diodes and no transistors. So these are a little bit simpler. If you need a logic gate real quick, the problem with doing diode-based logic gates is that the diodes don't typically switch as fast. So anyway, let's start with the bottom one. The A input, the B input, the output is this LED. So both these circuits, the diode with the lightning coming off of it is the lightning diode. More specifically, these arrows indicating the light should be pointing out. There are diodes that have light arrows in, and those are phototransistors that activate the light. Anyway, diode is going to be our output. So I start off with A and B both at 0 volts, so logical to 0. Both of these two diodes are not able to conduct as you need to have a higher voltage at the back end. So the LED does not light up. Turn A on, but leave B off. Whenever I turn on one of these inputs, that's like putting it at a high voltage. Now I'm forward biasing the top diode. Current can go straight through. There's enough voltage left over to activate the LED, and that lights up. That's on. Leave A off, turn B on. Same thing happens. Turn them both on, and the LED lights up. B or B. So that's a logic OR gate based on diodes. Top one is a little bit trickier to go through. Start with the case where both A and B are 0, so they're low voltage. So you can think of this being logic level low as having a path to ground. So the A and B are both low. This is where it gets a little tricky for me. A and B, or at least A, they're both high low. When the current gets to this point here, it can go. Got a choice. You go to there. You also branch from down there. There we also have two options. Having A and B both 0, having an extra resistor here with the LED. It's going to mean that even with by tying both of these low, effectively, let all the current go through these diodes and not through it. So that stays off. So in this top circuit, these two gate LED, these two gate diodes are essentially there to let current go through or not. They're effectively acting. Okay. So make A logic level high. If I do that, then it's reverse biasing this top diode, which effectively turns it off. But you still have B tied low, so the current will still bypass the delay emitting diode. So B, it stays off. Symmetric for 0, 1 still stays off. Make A and B both logic level high. Then what we have here at this junction is a higher voltage, and it is enough to forward bias sliding diode on. And we made this only turns the LED on for A and B. That's an AND gate, just with guidance. Questions, comments about that? So one more logic gate. How do I go from how do I get a NAND gate out of this? The way you turn the diode AND gate into the diode NAND gate. Remember, we need to do the exact opposite of this. So to make our AND gate the NAND, this LED that I just erased, it was this. That guy was here. And making an AND gate, you just flip the polarity of that diode. And that ends up having the effect of flipping all of these polarities. And you gotta do one more. You have to this ground needs to be on the other side of the element. So the ground that was back here, the front side that was positive. That's a diode named gate. And its truth table would be the exact opposite. All right. Okay, so to end up, to wrap up the flip-flop material, I'm going to go through two more kinds of flip-flops. We already talked a little bit about JK flip-flop. I'll tell you a little bit more about that. Before we get to that, I want to talk about T flip-flop. And T is for toggle. So we make the toggle flip-flop out of an SR latch, just like we made the data flip-flop out of an SR latch. The toggle is very similar to the data flip-flop. In the sense that we've got both the data or the toggle signal in ends up going to both the set and reset. So what happens with the toggle flip-flop, whenever T goes high, so logic level high for the toggle input, Q and Q bar change states. If T is logic level low, the output doesn't change. So it does just what it says. Every time you make T go high, it toggles the outputs from a lot of these gates are available like as an integrated circuit that you can buy, and it does all this stuff for you. Toggle flip-flop is one that usually you can't find pre-made. Yeah. You have to just wire it up yourself from SR flip-flop or some other. And here's where this can be useful. So every time I make T go high, I'm going to flip the output. So we can use this almost as a counter. If we're okay in counting in binary. So this is not a counter, this is a frequency divider. But it's just multiple toggle gates that are inserted. So what's going on is our first flip-flop, first toggle right here. That's the one that's getting a repeating clock pulse. So that clock signal going in is just an infinite string of square pulses on, off, on, off. Every time this gets clocked, the trick here is that Q bar output from the first toggle gate, this goes back into T input. So whenever this flips Q, that's going to change T. So T is also alternating between low and high, but at half the rate. We're getting a toggle, getting the opportunity to toggle every time the clock pulse flips in. But I'm flipping T between 0 and 1 at the other pulse. So that means that the frequency that I get out of Q, when I measure the Q output, that is half of what it is. So then they keep chaining these together. So if the output from the first one is half the frequency, if I duplicate that over here, it would fourth the frequency, so you can keep dividing down signal into dividing. Back to the JK flip-flop. So this is schematically what's in the inside of this flip-flop. A lot of AND gates and inverter. So the way that this is set up in this particular version of JK flip-flop is my clock signal here. I'm going to trigger the master flip-flop first. This clock signal also goes down here and gets converted, and it goes to the second flip-flop. Since this is inverted, that means this second one will happen after the first one. Whenever the clock signal goes back down to the low level, the inverted one goes back high, so that will trigger the slave portion set. Schematically, this is what it would look like on the circuit schematic. The two other inputs, PR and CLR at the bottom. Those aren't indicated here. Those are like a set and reset function. PR is like program. CLR is clear. So the top and the bottom inputs allow you to configure the initial state however you want. Clock, the CLK is the clock input, and then you have the two signal inputs, J. The naming for this one is kind of weird. The SR latch that extends set, reset, SR. Toggle is T, data is D, Y is a JK flip-flop, JK. That's named after Jack Kilby. There's your J, A. He was the guy that had a big hand in inventing the integrated circuit. So basically, he built a thing that had multiple transistors integrated into it. Not too long after the transistor was developed. So this is a long time ago. His first integrated circuit looks like, I don't know, garbage with some wires coming off of it. It was like a piece of germanium or piece of silicon. And he was able to process into enough transistors into it so that the story is that when he demonstrated it for his boss, it was a slab of silicon and he put it up to the oscilloscope that signed it. And that was like a big deal. Like he built a circuit onto a slab of silicon. Much later, he ended up sharing the Nobel Prize in Physics for that. If that name sounds familiar, Jack Kilby, you might be thinking of Socrates. Jack Kirby, the comic book guy that came up with like everything, Fantastic Four, all those comic books. Jack Kilby was JK book guy. So we're not going to go through how to generate this truth table. We're just going to skip to this is what it is. Basically, if J and K are different, 0, 1 or 1, 0, and when the next clock pulse comes in, Q gets what J is, and Q bar gets what K. You can see when they're opposite inputs, just kind of gets passed. So there's essentially, in a sense, no change. But if you make both high, so 1, 1, the Q final becomes the opposite of the initial state. Let's make them both high. Flip states. So different, and it just passes those same states. So this is kind of like letting you set inputs for say J, K. Both 0 on the input. That is just like setting, leaving it in its unchanged state. This 0, 0 doesn't. So I'll give you a couple quick applications for the JK flip-flop. And this is how you get a toggle flip-flop. Pretty much anything that you need logic-wise, you can build out of JK flip-flops. Toggle gate, all you have to do is short together the JK inputs. Whenever toggle go high, JK are both high, what's the state? If you can make a toggle gate, you can use that JK based toggle gate to make a frequency plug. It's the same thing as before. It's toggle gates in series with each other where the output of one toggle gate becomes the clock of the second. So this becoming this one's clock is effectively the thing that's dividing down the. This thing here is also a binary. And try and walk you through that. Okay. So we're going to be interested in these clock pulses. So we're going to start off and just kind of go down in the vertical slice. So this is our base frequency. So this is the one where I want to see how my states change in this first output from low to high. Zooming in like that. I'm going to try and recreate the first couple sequences. Here's the top one. And if you pay real close attention to how this bottom one lines up with the top one, Bottom one is low for 2 full cycles of the top. Goes high for 2, down, low for 2. I'm just trying to give you a better picture of what looked like. The third one is going to be low for 1, 2, 4, high for 2, 3, 4. How is this account? I'm going to think of my 4 outputs, A, B, C, and D, as my 4 places of a binary number. Right. So very first one is low, 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 low. That is 0. Then the first flip-flop goes high. 1, 0, 0, 0. This one goes low, but now the second one goes high, so I'm going to have 1, 0, 0, 1, 1. Back down to 0, back down to 0. Now we're high in the third one. 0. So what does this look like? First number I did was 4 zeros. 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0. So I'm counting through binaries. So if I look at all 4 outputs, A, B, C, and D, that gives me a binary number of what the count is. So toggle flip-flops built using a JK flip-flop. 4 of those are implementing a binary. How high does this count? One, 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 one. Whatever that is. That is binary. You count from 0 to 50. You count 16 spots. So what if you're not a computer and they really bug you to count in binary? You want to, like, when I get to 9, I want the next thing to be 10, not 8. You can do that pretty simple. So this thing is called a decade counter. It's just what I showed you before. Right? It's 4 flip-flops where the output of one is the clock to the next one. What's going on here is this extra NAND gate. And that is on flip-flop 1. This one. So you want to NAND these two together. Seven. 1008. 1001 is 9. What I want to do is, at this point, I want to reset. So by NANDing together, n would be this is 9. 9. 1010 would be where you want to restart. So if we NAND together, it's 2, force it to out 0, back to 1, and clear everyone. So if you want to stop the binary coming in before you get 16, you've got to find a way to pick out which one you want to stop at and stop it. Last one I wanted to talk about for today is a shipment. Pretty simple hookup. The Q output goes to J for all of these. So they're in series, but they're all getting the same clock cycle. So the clock cycle doesn't change. They're all moving at the same time. So what happens is I can input any data that you input to the first one. When a clock cycle or clock pulse hits the whole thing, the effect is that whatever was in D flip-flop gets shifted into C, C gets shifted to B gets shifted into A gets just put out someplace else. So all this does is it shifts data bits, shifts them all one way to the right or all one way to the left. And there's different versions of these. Shift right, shift left. This might not seem like this is useful at all, but being able to shift all your bits by multiple places, that's a key ability for doing binary computations. If you get down into the real nitty-gritty of how your computer is doing calculations, it's not smart at all. The very basic stuff that it's doing at the binary level is shifting bits around, and it does calculations by the only calculations it can do is add. How how can you do, how can adding how can that give you almost any calculation?
I saw somebody talk about this one. It was like adding, if you add negative numbers, you can subtract or something like that. And then,
Hold on. All right, so add the negative. The way you make a negative number, if you're working in binary, is graph like this, shifting bits around. Okay, how do you do multiplication?
it's like adding the total over number that.
But how would I do 3 times 2? 3, I'd add 3 twice. Repeated addition is multiplication. Repeated subtraction is division. That's what your computer is doing when it's trying to do stuff. Is it's not multiplying like how we're multiplying. It's doing some sort of binary implementation of that, and that really comes down to you're just adding.
Do we know where like binary is from? Who was the founding father of binary to open gates? So,
Like digital computing, or
yeah, like just like who came up with that idea? That from zeros and ones you can do. I mean, I'm sure it wasn't like, I'm sure they didn't think like you could create Google from zeros and ones, but
I think it's Charles Babbage, British guy, came up with the chemical computer. Kind of works that way. Yeah, it was when they started, when they could build vacuums. That was really that made it possible to build a lot. If it wasn't like, I don't know, I think transistors came along way before we got to this level. That like getting to this level of complexity was helped by transistors. Like being able to have a whole bunch of stuff on a small circuit instead of a room full of high voltage vacuum. It's interesting. A computer architecture class will give you more into that if you wanted. It's I think it's interesting, but it's a really hard way of programming. The computer's doing that's stuff like you have to tell it. Put this in memory address over here. And then remember where you put it to do something to that data, then pull it out of it. So you can't, it's not like
you can't assume anything. Like you can assume it can do like it's
yeah. You can also write with these simple programs, you can also write stuff where code and data are stored in the same place. So you can write a program that changes itself down the road. It's not compiled, it's just going like, I'm going through each step. Look at this memory location, what's there to do, go to the next one, what's there to do. This one it could say change what's 3 steps down. That could be a new program. You can write real messy code that gets.
You ever
TV
watch,
talk, so,
you ever watch Snowden?
watch what?
Snowden? The guy that.
Yeah, I know who he is. No, I haven't watched.
Yeah, the movie's pretty crazy. Like he's just like an insane coder programmer guy, and like he writes like these just insane amounts of code program that basically like are make like cybersecurity systems and stuff.
I have seen a video that he did on how to fix your phone's microphone so it doesn't like listen to you. And it's pretty much gonna crack it open and look at the solder the microphone out of the phone together. Like it's a complete, we're gonna disable this part of it. So there's no, you can't talk on it, but you can still, yeah.
I do find it weird that I haven't searched anything on my phone and then it starts bringing up like things I was talking to like my friends about like, out of nowhere. Like not once did I even type it into my phone at any point. And it's bringing it up like in ads.
If you are using a free service